Welcome to part 1 of double integrals and volume over a general region. By general region, we're talking about regions that are not rectangular. We've already discussed the limit definition of a double integral to determine the volume under a surface, so let's go ahead and take a look at how we're going to deal with regions that are not rectangular. If the region is bounded above and below by a function of x, then we'll have to integrate with respect to y first, where the limits of integration with respect to y will be g of x to h of x. And if our region is bounded to the left and right by functions of y, we'll first integrate with respect to x, and our limits of integration will be g of y and h of y. Let's go and take a look at our examples. We want to determine the volume under the plane z equals x plus y, and our region of integration is defined here, where x is in the closed interval from 0 to y over 2, and y is in the closed interval from 0 to 6. So it's important for these types of problems that we graph our region of integration. So let's take a close look at this interval here. We know x has to be greater than or equal to 0, but x also has to be less than or equal to y over 2. So if we know x is greater than or equal to 0, we're talking about the positive x-axis here. Let's take a look at this inequality here. If we were to solve this equation for y by multiplying both sides by 2, we would have 2x less than or equal to y. Let's go ahead and flip this around. This is the same as y is greater than or equal to 2x. So if we were to graph this inequality, we'd have a solid line here, but we would shade above the line. So that tells us the interval for x is going to be starting here where x is 0, and then moving to the right until we approach this line here. So it's a common mistake from this interval here to think it's going to be below this line, but it's actually above this line and to the right of the y-axis. And then y is on the closed interval from 0 to 6, so it's going to be this triangular region here above the line y equals 2x. This would be our region of integration. Now that we have our region of integration, let's go ahead and set up our double integral. And since the interval for x is given in terms of y, we'll have to integrate with respect to x first. So f of xy would be x plus y. Integrate with respect to x first, and then y. So for the limits of integration for x, we'll have from 0 to y over 2. And then for y, it'll be from 0 to 6. And so we mentioned this before. If we integrate with respect to x, the limits of integration would be in terms of y. So treating y as a constant, we're going to have x squared over 2 plus yx. And we need to evaluate this. Because we integrate with respect to x, we're replacing x with y over 2. So here we're going to have 1/2 times y over 2 squared plus y times y over 2 minus, and then when x is 0, these will both be 0. So let's go ahead and clean this up. Here we're going to have y squared over 8 plus y squared over 2. So if we get a common denominator of 8, this is going to be 5y squared over 8. Let's go ahead and take this on to the next slide. Now we'll integrate with respect to y. We'll have 5/8 times y to the third over 3. We'll evaluate this at 6 and 0. So we're going to have 5/24. And then when y is 6, we'll have 6 cubed. And then when y is 0, we'll have 0 cubed. So we have 5/24 times 6 to the third. I've already worked this out. It comes out to 45. And because this represents the volume under that plane, this would be 45 cubic units. Let's take a look at a graph of this. In red, you can see the region of integration. And then I've bounded that region by these yellow planes. So what we just found was the volume under the purple plane bounded by these yellow planes. And that was 45 cubic units. Let's take a look at another example. Here we want to determine the volume of the given function in the region where x is on the closed interval from 0 to 1 and y is on the closed interval from x squared to x. Let's take a closer look at this interval here. This compound inequality can be written two ways. Starting from the center moving to the right, we have y is less than or equal to x, and then from the center to the left, we have y is greater than or equal to x squared. So y would be below the line, y equals x, and above the parabola, y equals x squared. And x is on the closed interval from 0 to 1, so our region of integration is this region here between the parabola and the line. And again, this was the point 1, 1. Notice this region is bounded above and below as well as to the left and right by these two functions. But since we have y in terms of x, we'll integrate with respect to y first this time. So our function is xy. We'll have dy first and then dx. So y expressed in terms of x will be from x squared to x, and x will be from 0 to 1. So now we'll integrate with respect to y, treating x as a constant. So we'll have x y squared all over 2 in our limits of integration. Because we integrated with respect to y, we're replacing y with x and x squared. So when y is equal to x, we'll have x cubed over 2 minus, and then when y is x squared, we'll have x to the 5th over 2. Let's go ahead and finish this on the next slide. So we'll have 1/2 times x to the 4th over 4 minus 1/2 x to the 6th over 6. We'll evaluate this at 1 and 0. Let's clean it up first though. We'll have 1/8 x to the 4th minus 1/12 x to the 6th. So when x is 1, we'll have 1/8 minus 1/12. And then when x is 0, we'll have 0 minus 0. Our common denominator would be 24. So we have 3 24ths minus 2 24ths. That'll be 1 24th. And this would be the volume under that surface over the defined region. Let's go and take a look at this one graphically as well. You can see this outlined in red as our region of integration. So the value that we found was the volume of this region here below the purple surface bounded by this region in yellow. And it was 1 24th of a cubic unit. That'll do it for part 1. We'll take a look at some more examples in part 2.